Water moving across the Earth's surface is governed by relentless logic. It must flow downhill, aggressively exploiting the path of least resistance to get there. From a top-down satellite view, the resulting landscape often appears to be a chaotic tangle of ridges, valleys, and jagged topography. But if we strip away the forests, the topsoil, and the cities to isolate only the flowing water, a distinct geometric pattern emerges. These branching blue lines serve as highly structured physical manifestations of unseen geological forces. By learning to read these two-dimensional surface shapes, we can reverse engineer the three-dimensional tectonic history of an environment without ever needing to drill. To understand how to read these patterns, we need to isolate the variables by building a landscape from the ground up. We start with a baseline, a perfectly uniform solid block of impervious rock with a gentle, consistent slope. This environment possesses uniform lithology, meaning the rock type is consistent throughout. As water moves down this slope, it encounters no sudden hard spots or structural weaknesses to deflect it. Because the resistance is perfectly even, the water naturally collects and merges into a mathematically efficient tree-like structure. This establishes our primary rule. Uniform branching represents undisturbed geology. Any deviation into sharp angles or circles implies a significant disruption in the bedrock below. When simulated rain falls on our uniform block, initial runoff streams begin to carve shallow channels into the smooth surface. These smaller contributing streams act like the twigs of a tree, funneling downward and merging into larger master tributaries or branches. We call this tree-like network the dendritic drainage pattern, the most common baseline geometry on Earth. Dendritic systems develop over non-porous, uniform bedrock like granite or shale, where the water faces equal resistance in every direction. In the real world, dendritic flow cuts straight down over time, carving these classic, steep V-shaped valleys into the uniform rock. We can modify this baseline by tilting the uniform block model into a severe, steep regional slope. This extreme gravity forces the water to accelerate, stretching the streams out and forcing tributaries to flow side by side rather than branching outward. This stretched geometry is known as the parallel drainage pattern. In nature, parallel patterns are a common sight on newly emerged steep coastal plains, where uniform shelves of land have been rapidly uplifted. Both dendritic and parallel patterns are variations of the same rule: uniform geology simply reacting to the angle of gravity. To break that uniform baseline, we introduce tectonic stress, applying immense tension until the bedrock snaps. This tension shatters the uniform rock into a distinct grid of intersecting joints and fault lines. Over millions of years, physical weathering exploits these fractures, widening the faults into long, narrow clefts. Surface runoff is captured by these deep faults, forcing the water to abandon its natural tree-like path to follow the cracks in the crust. This forces smaller tributaries to join the master streams at stark, unnatural 90-degree right angles. This rectangular drainage pattern serves as a surface map for the deep faults below, as shown in this schematic proof. To a geologist, a river network composed of sharp right angles is a definitive signature of shattered, faulted bedrock. If we compress the crust with lateral force instead of tension, we see a different kind of structural deformation. This crushes the terrain like an accordion, creating a series of parallel mountain ridges and deep valleys, or synclines. This folding exposes alternating bands of hard rock and soft rock side by side. Primary rivers carve straight down the soft rock valleys, establishing massive channels that run perfectly parallel to one another. Meanwhile, secondary tributaries plunge aggressively off the hard rock ridges to join the main rivers at right angles. This unique combination of parallel mains and right-angle tributaries is called the trellis pattern. This geometry is the ultimate diagnostic fingerprint of historic, violent mountain building events. Beyond regional tectonics, extreme localized elevation changes create their own distinct signatures. Imagine a sudden central uplift, such as a magma chamber pushing up a dome or a volcano forming. This isolated peak acts as a central distribution point, forcing all streams to trace outward like spokes on a wheel. We call this the radial pattern, the classic signature of a standalone peak. When the crust collapses into a crater or tectonic depression, the rivers behave in the exact opposite manner. Water reverses its behavior, converging inward from the surrounding highlands to form a central basin. This is the centripetal pattern, the mirrored opposite of the outward radial flow. If we advance time by millions of years on our domed mountain, erosion will eventually shear off the top. Slicing the top off a dome reveals concentric rings of hard and soft rock layers. Streams will hunt for the softer rock layers, flowing in circular paths around the mountain to create an annular pattern. Perfect circles or radiating lines in a stream network instantly pinpoint the location of extreme geological uplifts or collapses. These structural geometries can be viewed side by side as a single diagnostic matrix. We can contrast the untouched, uniform branching of the dendritic model against the compressed, folded structure of the trellis model, or the shattered right-angle grid of the rectangular model against the centralized peak of the radial model. These two-dimensional patterns provide a vital diagnostic toolkit for civil engineers and geologists. Interpreting these angles allows analysts to accurately map underground conditions purely from satellite imagery, saving massive amounts of time and resources. Water does not carve the landscape randomly. It simply traces the structural blueprint already written in the stone beneath.